Hello. Today I'm going to teach you how to draw Lewis structures systematically. What I mean by that is I'll have a list of steps in which you can follow that will work for pretty much any basic small molecule. The larger the molecule gets, the more you're going to have to think about structure and think about it in terms of puzzle pieces and how everything fits together in order to get its 8 electrons. But this method that I'm going to teach you here should work for most smaller molecules. And as practice, we're going to draw OF2, NO3 minus, and NH4 plus. So step one, sum the valence electrons of each atom involved. So for OF2, we have an O and two Fs. O has 6 valence electrons, F has 7, and there's 2 of them, so we multiply it by 2, 6 plus 14, we get 20 electrons. These other two are a little bit more complicated. If the charge is negative, we're going to add the electrons to the total. So for example, NO3 minus, we had 5 valence electrons from the N. We had 6 from oxygen times 3. And then since the charge is negative, that means we have an extra electron on the molecule. So we're going to add plus 1 to a total of 24. If the charge is positive, that means that it has one less electron than we would expect. So we're going to subtract that from the total. So for NH4 plus, we have 5 from the N, 1 from each of the 4 hydrogens, and then we're going to subtract 1 from the total. So we're going to end up with 8 total valence electrons to use for bonding. So first we're going to draw a skeleton. We're just going to make some simple single bonds to connect everything to try to figure out what the layout of the molecule is going to be. And there's sort of one big thing you want to consider here. You're going to put the least electronegative atom in the center. And if you're not sure which one is the least electronegative atom, another way of thinking about this is put the one that can make the most bonds in the middle. So let's look at the examples I have here. So for OF2, I made a structure where I connected the O to 2 of the Fs. Just as a quick note, I drew this kind of vertical. If I was to draw this horizontal, that would mean the exact same thing. It's just rotated. So don't worry too much about how you're laying it out as long as the connections are correct. So O is less electronegative than F, and it can make more bonds than F. F tends to make only 1. O can make 2, sometimes 3. So we put O in the middle. So we have a single bond connecting each O to each F. And we're just going to leave it there for now for step 3. For NO3 minus, put the N in the center, single bond to each of the O's. And then for the NH4 plus, N in the middle, single bond for all of the H's. Now, this one was a little bit tricky because it's kind of hard to tell which is more electronegative, N or H. N tends to be pretty electronegative, but N can tend to make more bonds than H. H can only make 1 bond, so it can never go in the middle. Also for this one, you'll notice that N is making 4 bonds rather than the 3 that we would normally predict. I kind of talked about this last time, but N can break the rules a little bit sometimes. So the other thing we want to do here is to take note of how many electrons we used so far, because we had our totals 28 and 24, and with each step we're going to be adding more bonds and more electrons to the molecule, and we want to subtract those in order to make sure that we're doing this correctly. So for this one, for OF2, I made 2 single bonds, and each bond, if you'll remember from last time, is a shared pair of electrons. So each line I drew counts as 2 electrons from the total. So that's why I subtracted 4 from the 20. So we're going to have 16 left for this one. For this one, I used all 8 already. So this one has already run out of electrons. And that's not a problem. Like we'll look at that in a sec and make sure that our molecule is correct. And then for this one, I made 3 bonds. That's a total of 6 electrons being subtracted from the total. All right, now we're going to add electrons to the surrounding atoms until each has an octet. Remember that an octet means having 8 valence electrons. So for this one, just as a quick note, also we add the electrons to the surrounding atoms first, because the assumption there is that the outside atoms are the more electronegative ones, and more electronegative things tend to pull electrons towards them. So they're going to get kind of first dibs on the electrons. So for OF2, each of the Fs already had 2 electrons because they had a single bond with oxygen. So then to get to 8, they needed 6 more. So 2, 4, 6. 2, 4, 6. That's another 12 electrons that I've used. So we're going to subtract another 12 from the total. So that means we have 4 electrons left for this molecule. This one, we didn't need to do anything because we were already out of electrons. And then for this one, I added 6 to each of the oxygens because they each had 2 because they had a single bond with nitrogen. So that'll be 6, 12, 18 now being subtracted from the total. And we're out of electrons on this one too. So next step, just as a quick note here, in terms of octets, remember that hydrogen only needs 2 because it only needs 2 to fill its first 1s subshell. Boron is a really weird example. Boron, if it ever comes up, only needs 6 electrons to be satisfied. So just take a note of that. All right, step 5. Now we're going to add any remaining electrons to the center atom. So if you'll remember on this one, we had 4 electrons left because we had 20. We subtracted 4 at first to make the 2 single bonds. Then we subtracted another 12 to give each of the fluorines its octet. And then we had 4 left. So I put those 4 on the oxygen as lone pairs. And then for this one, we didn't need to do anything. We were already out of electrons. And for this one, we didn't need to do anything because we were already out of electrons. Now, for step 6, if the central atom has fewer than 8 electrons, meaning it doesn't have an octet yet, it doesn't have the 8 valence electrons that needs to fill its subshell, or its valence subshells, then we're going to need to do a little bit of a trick here. I kind of mentioned before that lone pairs don't normally make bonds, but there is an exception here, because if the central atom doesn't have enough electrons, one of the outer electrons is going to sacrifice one of its lone pairs to make another bond. So probably a double bond, sometimes a triple bond, in order to make sure that the central atom has the 8 that it needs. So this one, oxygen has 2, 4, 6, 8. That one's fine. This one, the nitrogen has 2, 4, 6, 8. That one's fine. For this one, the nitrogen has 2, 4, 6. And I can't just slap another lone pair of electrons on the end because we are out. Because when we did 2, 4, 6, and then 2, 4, 6, 2, 4, 6, 2, 4, 6, that was a total of 24 electrons. We already used up all of our electrons. And this nitrogen still isn't happy. It doesn't have 8. So this is where this is going to apply. Now, in the example here, I pulled one of the lone pairs off of this oxygen and then turned it into a double bond with the nitrogen. And this works out just fine because this oxygen has 2, 4, 6, 8, and then now this nitrogen has 2, 4, 6, 8. So this one is good now that we've switched that lone pair over to another bond to make a double bond. And let's just take a look at everything, make sure everything's good. We already checked this one, 2, 4, 6, 8, 2, 4, 6, 8, and then we already checked this one. So all of these molecules look good now because all of their atoms have 8 electrons, unless they're hydrogen and they have 2, which this one also applies there. Each of these hydrogens look good. Another note, if you have period 3 elements like phosphorus, sulfur, and chlorine, those ones have D subshells available to them, so they can do some weirder stuff where they can make more bonds than you'd expect. Like they can get up to 12 valence electrons in their valence subshell, but don't worry too much about that right now. Okay, and then the rest of this slideshow is just a bunch of practice problems. I have included the answers for each of these. I highly, 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 highly recommend that you go through these and try to practice each one, because this, more than a lot of stuff, well, I guess with the exception of stoichiometry, is one of those skills in chemistry that you just need to practice, practice, practice in order to get a good feel for it. So good luck. Let me know if you have any questions.